Okay, we return another integral from the UK integration bee. This is sample problem number 4. We have the integral from 0 to infinity of natural log x over x squared plus 1 dx. Okay, I actually know two different ways to do this. One's the quick way, one's the long way. And I don't really have a preference. I like both of them, so I think we'll do two videos on this. But for now, let's just start with the quick method. And the thing I notice here is with this denominator, this is just the situation where you could do a trig substitution. The only thing that's unusual is we're not used to really doing a trig substitution with natural log in the problem. But it's still going to work pretty nice. So what I'm going to do is for this substitution, we'll just set x equal to tan of t. Then let's solve for t. So we'll take the inverse tangent on both sides. We'll have t is going to be arctan of x. Then taking a derivative on this first term, on this first equation, we end up with dx is just equal to secant squared t dt. So we'll go ahead with this first. Let's update our bounds using this one here in the middle. So when you look at infinity, arctan at infinity is going to be just pi over 2 for the upper bound. And then for 0, arctan at 0, that's just 0. Then this numerator, that's just going to become ln of tan of t here. Then this here, this is going to become tan squared t plus 1. And then for our dx, we have this. And you might see where it's going because for this in the denominator here, we've got a nice identity. This is the same thing as secant squared t. So then if we just transform it like this, we're going to get some cancellation. This is going to cancel with this. And then we've got a simpler problem, just natural log tan of t. Now for tan of t, of course tan of t is the same thing as sine of t over cosine t. So with a fraction inside the natural log, what I can do is we can break this up because if we have natural log sine t over cos t, this can be written as natural log sine t minus natural log cos t. So we'll do this, make this update. And now from here, if you're used to doing a lot of problems with King's principle, I think you'll see where it's going because we have sine and cosine, and we've got our bounds going from 0 to pi over 2. What this tells me is this solution is actually just going to be 0. But I think we just need to show a little more work to see why this works. So for King's principle, our formula over here is just going to be if we have an integral from a to b of f of x, that, of course there's a dx in there, that we can rewrite this as f of b plus a minus x. So in our problem here, our a and b values is just 0 and pi over 2. So we're going to be looking for f of pi over 2 minus x. So if we just do this really quick, the bounds stay the same. We're going from 0 to pi over 2. We end up with natural log sine pi over 2 minus t here. And then for this one, we're going to have minus natural log cosine pi over 2 minus t. But then from here, let's just use the complementary angle formula on both these. So sine pi over 2 minus t, this becomes cosine of t. And this one, the sines become cosines, the cosines become sines, and this becomes sine over t. But then what just happened is this is basically the same as this with the sign reversed. So we can just kind of put a couple of labels on things. Like if I label this one I, then this one here, this has to be minus I. And these two things have to be equal. We've got an equation. We're just saying I equals minus I. Add I on both sides. We end up with 2I equals 0, or I equals 0. Okay, there you have it. Good one from the UK integration bee. Thanks everyone for watching. Have a good day.